Hello. Hi. Right, so this is section 1.7 for Math 204. This follows on from what we've been looking at earlier on in the class and the videos. So in particular, in section 1.6, we looked at powers and roots. Of complex numbers. And this chapter is in some sense an extension of that. One of the important points from section 1.6 that are important for this chapter is that for any integer, I guess I should really say yes, I should really say this, right? So for every element of the integers, there's n complex numbers. So that Win is equal to z, where z is some complex number. And we discussed why this was true in the last section. One of the things that the interesting implications of this, and I've mentioned it, I think, in the actual lectures rather than in the videos, but one of the implications of this is something called the fundamental theorem of algebra. And that's what this section is about. It's just like in section 1.4 for Euler's formula. We didn't prove Euler's formula, but you saw it. And I'm going to state the fundamental theorem of algebra for you, and the proof will appear later on in the class. The fundamental theorem of algebra is a very important theorem to do with complex numbers, and sets it apart from the real numbers. So as you know already, C is a field. And R is a field. They satisfy the same algebraic rules. The fundamental theorem of algebra is false for the reals, but it is true for the complex numbers, and this is one of the things that sets the reals apart from the complex numbers, that demonstrates demonstrates a difference between them. So the fundamental theorem of algebra is a point of difference between them. Okay, so it's important to know what it is. So before I state what this is, let's go back and consider some other classes that we've had a look at. Some other results we've had a look at. In particular, lemma 1.7.1, which is a restating, really, of lemma 1.1.7. So this is an older result. So let alpha, beta be an element of the complex numbers. If z minus alpha times z minus beta is a quadratic in z, in the variable z, with real coefficients, then either both alpha and beta are in the reals, or beta is equal to the complex conjugate of alpha. The proof of this is good to see. And the reason why we're restating this provides a little bit of motivation, gives you, I guess, some evidence that maybe, just maybe, when I state the proof of the fundamental theorem of algebra, you will believe that it is true. Okay, so z minus alpha, z minus beta, is z squared minus alpha plus beta z plus alpha beta. So by assumption, we know that alpha plus beta is in the reals, and we know that alpha times beta is in the reals. So we want to let alpha equal a1 plus I a2, and I will let beta equal b1 plus I b2. And we'll just plug them in. Alpha plus beta is a1 plus b1 plus I a2 plus b2. So alpha plus beta inside the reals. Hi. Well, so the sum is in the real numbers, and that means that a2 plus b2 must be equal to 0. Similarly, we have alpha beta, the product of these things, must be a1 times b1, and then I times I is minus, so a2 b2 plus I times a1 times b2, and then a2 times b1. So the product, being in the real numbers, similarly implies that a1 b2 plus a2 b1 must equal to 0. Now, as a2 plus b2 equals 0, we know that b2 is equal to minus a2. So then a1 b0 is equal to a1 plus a1 times b2 plus a2 b1. Substitute in here, so that's minus a1 a2 plus a2 b1, which is equal to a2 times b1 minus a1. So there has been a fire alarm going off, and that's what all the beeping was about. And I will try and remove all the beeping from the video so that all you really hear is me talking about the beeping. But if you do hear beeping, I apologize. Right, so we have this equation equal to 0, and of course that implies that either a2 equals 0 or b1 equals a1. So if a2 equals 0, well, a2 is equal to b2, so that implies that b2 equals 0, and that of course implies that alpha is equal to a1 and beta is equal to b1, and that both of these are in the real numbers. On the other hand, if b1 equals a1, then as b2 equals minus a2, we have beta is equal to, well, b1 equals a1, and b2 equals minus a2, so it's minus a2, and so the complex conjugate of beta is a1 plus I a2, which equals alpha, and obviously I wrote the statement that, with the complex conjugate of beta being equal to the complex conjugate, with beta being equal to the complex conjugate of alpha. So let's just do that. We know that the double conjugate is equal to beta, so the double conjugate of this is equal to the conjugate of alpha, so then we get beta equals as required. So, pretty easy. Well, lots of algebra. Unfortunately, there is no purely algebraic proof of the fundamental theorem of algebra, which is interesting because it kind of hints that the complex numbers have something interesting about it. Okay, now here's a result. So based upon the one I just gave you, and really we've been operating under a kind of assumption of this because we have an explicit equation. But anyway, so a theorem. Every polynomial ax squared plus bx plus c with a, b, c, has a complex root. And the proof of this is fairly easy as well. You've seen this all before. The roots are given by we have an explicit equation for it. And we know how to take the root of complex numbers if needed, so we can work out what this is. And remember, if this works out to be a real number, well, the reals are also complex numbers because they're included, so that's okay. Right, and this leads in to the next theorem. This is the fundamental theorem of algebra. 1.7.3. Fundamental theorem of algebra basically says that this works whatever power you have for x. Every non-constant polynomial an xn plus an minus 1 xn minus 1 all the way down to a1x plus a0 with ai, an element of the complex numbers, for I equal to, well, 0 up to n minus 1, has a complex root. Just one complex root. Of course, we'll prove in a moment that, in fact, this theorem implies that a polynomial of power n should have n complex roots. But that's the difference between the real numbers and the complex numbers, because for the real numbers this is not true. In fact, we know this already, because we know that there are quadratics in the complex numbers that don't have two roots, or at least don't have roots of multiplicity. Counting that, we know that there are polynomials, quadratics, in the real numbers that have no roots at all. In the complex numbers, every polynomial has at least one root. And I'm trying to be very careful here because if I say has n roots, you need to interpret that correctly, in the sense that the polynomial x squared has one root, which is 0. But because x squared, you can write it as x minus 0 times x minus 0, we really say that this is a root of multiplicity 2, because it occurs twice. Another example, x minus 2 squared is x squared minus 4x plus 2. And we could say that this has two roots, well, it has one root, but that root occurs twice. Anyway, this will come up later, so don't worry about it right now. Anyway, this is why they're being careful by saying it has a complex root. The same number may be a root of, again. Anyway, don't worry too much about that. That will appear later in the course when we talk about it. So theorem 1.73 has a corollary. Corollary 1.7.3. Oh, sorry, 4. And this is perhaps the way that it might be more reasonable to talk about this. Every non-constant polynomial an xn plus an minus 1 xn minus 1 plus all the way down to a1x plus a0 with ai in the complex numbers I equal to 0, 1, all the way up to n has n roots, not necessarily distinct. Okay, and the proof of this uses induction and is worthwhile seeing. So, proof by induction. Let's do the n equals 1 case. So our polynomial is a1x plus a0. And this has the root minus a0 over a1. Take this, plug that into there, you get 0. Right? So a1 minus a0 over a1 plus a0. a1's cancel, minus a0 plus a0 equals 0. So that's a root. Great. a1's done. So now assume the result for n minus 1, for n minus 1, and let ai be an element of the complex numbers, and I equals 0 all the way up to n. Okay, so by the fundamental theorem of algebra, the polynomial an zn. Wow, I wrote x down here, didn't I? I was thinking of x as a complex variable. I'm sorry, that's a misuse of notation because I've been using x fairly diligently for real numbers. So here I'm thinking of x as an element of the complex numbers. Zn is an minus 1 zn minus 1 all the way down to a1z plus a0 has a root. Right, well that means that we can write an zn plus an minus 1 zn minus 1 plus down to a0 equal to z minus alpha times some other polynomial, bn minus 1 zn minus 1 plus all the way down to b0. How do I know this? Well, we talked about long division of polynomials in section 1.5, and you know that if there is a root of a polynomial in the reals, you can always write it this way, and we did long division in the complex numbers, and all the same thoughts and reasons that it works in the real numbers transfers over to the complex numbers, so this is fun. Okay, now by induction, there exists bi, let's say j, j, in the complex numbers. J is equal to 0 up to n minus 1, so that bn minus 1, zn minus 1 plus down to b0 is the product j equals 1 to n minus 1 of z minus beta j. So this stands for the product and can be written out z b minus 0, z minus b1, all the way up to z minus beta n minus 1. But then we have n roots. But then an z n minus n an minus 1 z n minus 1 all the way down to a0 has n roots, which are alpha and beta 0, beta 1, all the way up to beta n minus 1. And that's the end of the proof. So I never checked that any of these were different from each other, so we might be counting a root more than once in here. Right, so that kind of summarizes everything that's gone into sections 1.4, 5, 6, and and this is section 7. So sections 1.4, 1.5, 1.6, we're all kind of setting up this argument here so that you would be able to see at least how the fundamental theorem of algebra implies that every non-constant polynomial has as many roots as we would guess it has. It's an attempt to try and hint for you at a result that took a very long time to prove, and that gives a clue as to why the complex numbers are so interesting. Right, so on that point, the notes say that Cardano in 1545 invented complex numbers. I put invented in quotes because there's a philosophical discussion about whether maths is invented or discovered. Anyway, now the fundamental theorem of algebra was proven by Gauss in 1794. Gauss in 1799 proved the fundamental theorem of algebra. "254 years later." People will have had a pretty good guess that this is true. And I like to think that maybe, just maybe one day, I might be able to prove a result that is as like that, something that people have sought for a long time and have been wonderfully engaged with. So that's the fundamental theorem of algebra. So you've seen Euler's formula, which we don't have a good proof for yet, but we will have one later on. And you've seen the fundamental theorem of algebra, which we will give a good proof to later on as well. But they're both used to try and provide some better motivation and arguments for why complex numbers should be studied and why complex numbers are very interesting. That's section 1.7.